Our third and final illustrated example problem features a series combination of two elements. The first element is a non-ideal 120 millihenry inductor that includes a small internal resistance of 10 ohms. The second element is a 100 ohm resistor. The source has an effective value of 208 volts and an excitation frequency of 60 Hz. We're again being asked to solve for the voltage drop across each element, the current through each element, and the source current. By all means, pause the lecture and try this on your own. If you're tracking, you should obtain the following results. The complex impedance of the non-ideal inductor requires a series of calculations. The complex impedance of the resistive portion of the non-ideal inductor is 10 ohms at an angle of 0 degrees. The complex impedance of the inductive portion of the non-ideal 120 millihenry inductor at an excitation frequency of 60 Hz is 46.3 ohms at an angle of 77.5 degrees. The resistive and inductive portions of the non-ideal inductor are in series with one another. In totality, the non-ideal inductor presents a complex impedance of approximately 46.3 ohms at an angle of 77.5 degrees. Let's call this impedance Z1. The complex impedance of the 100 ohm resistor is 100 ohms at an angle of 0 degrees. Let's call this impedance Z2. A Kirchhoff's voltage law analysis of the loop within this series circuit suggests that E equals V1 plus V2. Additionally, given there is a single path for current in this series relationship, it can be stated that source current IS equals I1, which equals I2. If we solve for source current or current through any single element, we by extension also solve for current through all remaining elements. There are several ways to obtain the desired figures. This time, let's go about it by solving for total impedance. Z1 plus Z2 yields a total impedance of 118.9 ohms at an angle of 22.4 degrees. Application of Ohm's law, supply voltage over total impedance, demonstrates that source current will be 1.7 amps at an angle of negative 22.4 degrees. The phasor diagram for the complete series circuit illustrates that source current appears to lag supply voltage by 22.4 degrees. Given that this is a purely series circuit, it can be said that IS equals I1, which equals I2, which equals 1.7 amps at an angle of negative 22.4 degrees. Current through elements in series is the same. Application of Ohm's law solving for V1 demonstrates that voltage across primarily inductive impedance Z1 will be approximately 81 volts at an angle of 55.2 degrees. The phasor diagram for primarily inductive impedance Z1 illustrates that current appears to lag voltage by a relative 55.2 plus 22.4, or a relative 77.5 degree phase shift. A purely inductive element would experience a full 90 degree phase shift. Finally, application of Ohm's law solving for V2 demonstrates that voltage across resistive impedance Z2 will be approximately 174.9 volts at an angle of negative 22.4 degrees. The phasor diagram for purely resistive impedance Z2 illustrates that current and voltage appear to be in phase with one another. As a means of checking our work, note the summation of V1 and V2 accounting for magnitude and direction yields a total applied voltage of 208 volts at an angle of 0 degrees. I've got a reasonable degree of confidence our answers are correct, and we can bring this lecture to a close. In conclusion, this lecture examines several illustrated examples of series AC circuit analysis. Remember to practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.